Hi, my name is Adam Boss, and this is my public lecture review on ultra short pulses. I don't exactly remember the public lecturer's name, but I took it on October 24th in Culk Room 151, I believe in. It wasn't in the archives, but that's all right. So the summary, an ultra short pulse, or what I learned, is obviously a very small fragment of a pulse, specifically used as a measurement of time. That's really the whole idea. The biggest part of the lecture was the technology behind how to create these ultra short pulses, but the main principle of these ultra short pulses is to be somewhat of a really small fragment of time, especially when you think about how these pulses are light, by the way. If you think about how quickly light goes, if you were to measure a fragment of the wave of light, like how quickly that wave moves, such a small fragment of it, it'd be a infinitesimally small, piece of time. Like, we're talking like 10 to multiple degrees smaller than a second, a lot shorter than a second. And this was actually related to the 2023 Physics Nobel Prize, which I believe was handed out to 3 people. Not the public lecture, but that's all right. And essentially, they were able to find, they were able to calculate ultra short pulses that were shorter, are within the time, I think, of femto or attoseconds, which is, don't remember the exact degree, but again, very small, like definitely larger than nano, the degree is larger than nano, but a lot smaller than nano. And FROG, which is an acronym for a certain machine that has been used for that. But essentially the 2023 Physics Nobel Prize was related to ultra short pulses. What did I learn? Well, one thing I learned was, when you want to measure something, this is what I found to be most interesting. If you want to measure something, you have to be able to have a unit that is smaller than it. Like, you can't, like, I would not be able to measure 1 second if I did not know it was 10 deciseconds, etc. Or you need to have a unit of time. So the thing is, the thing is, to prove these ultra short pulses, you kind of have to use them on themselves to prove how long of time it is. And by doing so, they're able to create pulses that were in like the femtoseconds, but like measuring it, you have to have something smaller than what something is in order to be measured. And I think that was what I found to be most interesting. Not necessarily, I did find the physics itself interesting, but I do believe that more of like, not the engineering part, but like the conceptual like application of why they have these is important. Of course, I also learned that waves behaved oddly and they propagate in such weird ways. I know the lecturer talked about a lot of difficulties that he found with creating even shorter pulses, and again, measuring how short these pulses were, because there were some inaccuracies. Sometimes the wavelength propagates or divides into multiple spectra, such as white light breaking into multiple different colors of light and having to, gather them back. But that's what I mainly learned. Like, he did discuss a certain extent on like the technology behind ultra short pulses, but what I found more intriguing was their application, and that leads me to my follow-up. And the biggest follow-up is like, why would I need to measure something that is a femtosecond? And a lot of things happen very quickly, but what is such that it has to be measured to like 10 to the 20th degree, or negative 20th degree to be specific. And I found out that they are looking at what are called quantum interactions in molecules. Molecules have molecular interactions, and their movements are very quick. And the relative positions of atoms in a molecule, for example, move very rapidly, of course, like extremely rapidly, within femtoseconds. And that's really the application of ultra short pulses, was to measure a period of time that is very, very short. And the biggest thing that occurs in nature that is that short are molecular interactions, or like temporary moments within the molecule.